everyone, my name is Rizana Vera and today I'll be introducing about our ABS control system project. So, road fatalities are most common occurrence today. So, during research in vehicle dynamics and control is advancing daily. New methods and approach are being discovered. So, one of these is the anti-lock braking system, the ABS. It is an active system that regulates braking related vehicle dynamics. So, by controlling wheel longitudinal slip at the ideal slip value, it achieves maximum braking force by doing this, and as a result, it controls the car while slipping and shortens the stopping distance. So, it guarantees direction stability and prevents vehicle skidding. So, when a heavy braking is performed, vehicle without ABS experience lockup conditions. When a tire becomes stuck, friction coefficient decrease below the sliding value. So when a tire locks, as a result, a vehicle's ability to withstand side force is completely eliminated. So as a result, stopping distance increase and a turning vehicle loses control. So consequently, the car loses control and derails, resulting in tragic collisions. So the goal of this project is to analyze and construct a control system using manual calculation and software application to solve a challenging engineering challenge. CB, which ideally students will use theory-based numerical analysis, technical knowledge, and industry-specific expertise to present their series. So the next is the scope. So this project will examine and analyze anti-lock braking system and control. And next is to become familiar with performing simulation work on the MATLAB platform and to understand how to do it. Hi, hello everyone, my name is Rizana Vera and today I'll be introducing about our ABS control system project. So, road fatalities are most common occurrence today. So, during research in vehicle dynamics and control is advancing daily. New methods and approach are being discovered. So, one of these is the anti-lock braking system, the ABS. It is an active system that regulates braking related vehicle dynamics. So, by controlling wheel longitudinal slip at the ideal slip value, it achieves maximum braking force by doing this, and as a result, it controls the car while slipping and shortens the stopping distance. So, it guarantees direction stability and prevents vehicle skidding. So, when a heavy braking is performed, vehicle without ABS experience lockup conditions. When a tire becomes stuck, friction coefficient decrease below the sliding.
Hi, my name is Gopinathan. My material number is CD200153. I want to present about here a literature review. So, anti-lock braking system can be traced all the way back to the 1920s, when engineers first applied the concept of an automatic override braking system to aircraft brakes. The system served the same purpose as modern ABS, preventing wheels from locking until during rapid deceleration or on low transvection surfaces. ABS remained primarily in aircraft technology until 1950s, when it was applied to motorcycles, since skidding and losses of traction present a major safety risk to a motorcycle driver. This became a natural place to adapt the technology. So, since the ABS modern invented in 1990s, the system works by sensing the rotation of each wheel and pumps up the brakes for the driver while maintaining the wheel speed according to the optional speed needed for instant braking. In fact, most tests confirm that ABS minimizes the risk of accidents, especially on slippery or wet surfaces. In fact, the presence of ABS technology can actually help lower auto insurance costs. That's how effective it is. So now we want to see about the substance of anti-lock braking systems in vehicle. So first, ABS in motorcycles. So car dashboard indicating ABS, the light, and then the electronic control unit ECU, and the fourth is configuration for the four-wheel of cars. So now there are many sensors and activators in car. So I want to describe about 3 or 5 sensors. So the first sensor is ABS control module and hydraulic control unit inside the car, and then the two-way connector. Third is diagnosis connector. Fourth is ABS warning light. 5 is data link connector for Subaru selected monitor cars vehicle lah. Hello, I want to present about block diagram. Block diagram is a controller is very often used in industrial application with different variations. Controller works with closed loop, whereas input we consider error between reference and output of the system. The controller is considered as GS is a formula. So now we want to see about the open loop controller. And second one is the actuator loop of the system. The third one is the transfer function of the actuator in the system. Fourth is ABS loop controller. So including ABS loop controller, including the system transfer. So next we want to see about by using the feedback formula to reduce the block diagram and the transfer functions of and block diagram. For the anti-braking system for fully reduced form is as below. So this one is the equation Y bracket in S over R bracket in S equal to G bracket in S 1 plus or either negative GS and HS. So now we want to see about the diagram of the ABS system is fully reduced form. So in conclusion, the concept of transfer function is very important since it provides useful mathematical model of the system elements, the models dynamic systems. For the anti-locking braking system, it requires transmit signal for one variable to another. Under the closed loop feedback control system, the ABS system can operate well as the mathematical model of the system is determined by the system.
Hello and good day. My name is Selvin Presbarao and I would like to present about the transfer function and the block diagram of the system. So there's a transfer function here, which is as per the objective of the study, where the actuator will be formed when the pump and the valve in the system are merged to form a single transfer function, and the transfer function can be used in the analysis of root blockers, time and frequency response, as well as the analysis of the stability response. As for the rest of the analysis, there's a block diagram here. It's a convenient tool to visualize the system as a collection of the interrelated subsystem where the ABS loop system to the block diagram, which is to emphasize the relationship among the system variable. So this is the block diagram, and after that we image the both transfer function of the block diagram into one connected series where it can be reduced by step by step by using cascade block rule, which is shown here. There's a cascade block rule. Then we get the equation of the transfer function, which is K over Js to the power of 2 plus S times Js plus to the power plus 1. So there's a feedback here, which is the sensor K attach times S. So therefore, for the complicated block diagram, it can be treated step by step by applying the negative feedback rule, where the formula of the input is GS over 1 plus GS plus times with HS. So we get the formula of the transfer function, which is K over JS plus S times JS plus 1 plus KA times K dash times S. And this is, you can see here, this is the final transfer function of the block diagram reduced form, the ABS system.
Assalamualaikum everyone, my name is Rizana Amira and I'm going to present on chapter 3. So for the analysis, for the purpose of this analysis, the formula that will be used is moment of inertia multiplied by angular velocity plus rotational damping of the tire multiplied with angular velocity equal to t. So as we calculate, we will get 4.1 kg per square of inertia. Okay. So the moment of inertia is calculated from this value to be J equal to 4.1 kg per square, and the sensor gain K touch is assumed to be 25 in the analysis. This assumption is based on the fact that the sensor produces a low voltage. So in order to receive information from the sensor, the controller will require a higher voltage signal. As a result, the voltage from the sensor must be amplified to resulting in high gain. So in the controller analysis, the actuator gain K actuator is assumed to be 0.25. This is due to the hydraulic system high pressure. So to achieve the desired pressure at the braking system, the valve and the pumping system will not have to do much work. So next, we're going to translate all of the information we get into a transfer function. As you can see, this is our transfer function. After we get our transfer function equation, we will substitute our K actuator equal to 0.25 and K tag is equal to 25, and we will get our S 0 and our poles as like the picture showed in the slide. So since we get 3 poles, we will calculate the angle of our asymptotes with our theta is equal to 0, 1, 2 and 3, and we will get the angle of 45, 135, negative 135 and negative 45, and we will get our characteristic equation like shown in the image on this slide. After we do some calculation and differentiation, we will make a roof table and plot the root locus diagram as shown in the slide. So the roots are in the left half of the S-plane and the system is open loop stable. So this is because there are no change in sign in the roof table. With this information, the root locus plot can be manually drawn from the mentioned data. Based on the root locus plot system, the system is open loop stable. We then compare our sketch root locus with the MATLAB generated root locus as shown in the picture below. So next, we'll be focusing on the transient response. For a system with a transient function GS, whether open loop or closed loop, and input RS, the output is shown in the picture next. So, since the transfer function is in a higher order system, it is difficult to calculate using the standard transient formula. Therefore, to test all the transient response parameter, we simulate the graph using the MATLAB program. The outcome are as follow. So, the transient response plot shows that amplitude increasing linearly with time. Because this is an anti-lock braking system, so the system signal response must change constantly over time. Next, we will do a frequency response graph, which is Nyquist plot, and from that we can sketch Bott plot using MATLAB. One of the tricks is also to use Wolfram Alpha to sketch the Nyquist plot system, as it will auto generate the Bott plot diagram. Based on the Bott plot of the system by using MATLAB program, it shows a stable manner of frequency response due to the phase margin is greater than the gain margin. That's all for me. Thank you.
Assumption of the gain of the sensor K tag is 25, J equals to 4.1, and the gain of the actuator Kx is 0.25. The closed loop transfer function of ABS of P controller is G bracket S equals to 0.25 kP over 16.81 S power of 3 and plus 8.2 S power of 2 plus S. So T bracket S equals to 0.25 kP over 16.81 S power of 3 plus 8.2 S power of 2 plus S plus 6.25 S kP. That's for equation number 1. So we assume that the value of kP equals to 250, 500 and 1000. The value of kP are substituted in equation number 1. So for the first value, kP equals to 250 equals to 62.5 over 16.81 S power 3 plus 8.2 S power 2 plus S plus 1562.6 S. Value 2, kP equals to 500. So T bracket S equals to 125 over 16.81 s power of 3 plus 8.2 s power of 2 plus s plus 3125s, and value 3, that is kp equals to 1000, so t bracket s equals to 250 over 16.81 s power of 3 plus 8.2 s power of 2 plus s plus 6250s. All the three graphs are linear with a proportional gain. So if the value of proportional gain is higher, the ability of the ABS system getting lower. So for kp equals to 1000, it is the best possible value that results in the fastest response time to achieve steady state condition without any overshoot in the system. As you can see in the graph, there will be infinite steady state error for the transfer function when kp equals to 1000. J equals to 4.1 kg per meter square. Mechanical Kx equals to 0.25 and Kp equals to 1 kg. So the closed loop transfer function is G bracket S equals to 0.25 bracket 1000 plus KdS over 16.81 s power of 3 plus 8.2 s power of 2 plus s. Let's go equation number 1. Hash bracket s equals to cat tag s, that is 25s. Let's go equation number 2. And t bracket s equals to 250 plus 0.25 kds over 16.81 s power of 3 plus 8.2 s power of 2 plus 6251s plus 6.25s bracket kds. Let's go equation 3. So all the values of kd are substituted in equation 1. So for the first value is 250 equals to 250 plus 62.5s over 16.81 s power of 3 plus 1570.7 s power of 2 plus 6251s. So for value number 2, that is kd equals to 5000. T bracket s equals to 250 plus 125s over 16.81 s power of 3 plus 3133.2 s power of 2 plus 6251s. For value 3, that is kd equals to 1000. T bracket s equals to 250 plus 250s over 16.81 s power of 3 plus 6258 plus 2 s power of 2 plus 6251s. So as you can see from the graph, there are 3 graphs with different value of kd, that is 250, 500 and 1000 are directly proportional to the proportional control. From this linear step response graph, sampling time for this closed loop cannot be determined. Thus, it can be observed that the derivative control has no effect on this ABS system.
As for the effect of the P, PD and PID controller, and I would like to explain the PID controller effect, where as you can see here, this transfer function diagram that we made from the previous explanation. The Kp plus Kd plus Ki over S, and then go to the Kx over Js to the power of 2 plus S times Js plus 1, then this will be back K attach times S. So in here we assume the K attach is equivalent to 225 and J is 4.1 and the actuator K for the actuator is 0.25. The closed loop transfer function of the ABS of the controller is 0.25 times with the Kp plus Kd plus Ki over S over 16.81 s to the power of 3 plus 8.2 s to the power of 2 plus s plus 0.25. I think the 0.81 S2 of 3 plus 8.2 S2 plus S, and then we substitute the GS into the formula, which is which is a GS over 1 plus GS times HS. So in here we get the final result question, not really the final result. We substitute all the value here, principal value here, which is the KP. The KP we assume is 1000. It says 1000, and as for the KD we use a 500 value, and for the final equation that we get is 0.25 times KP plus KD plus KI over S over 16.81 S to the power of 3 plus 8.2 S to the power of 2 plus S plus 6.25 S times KP plus KD plus KI over S. The equation 1 as shown in the previous slide. So we substitute all the value of the KI, 50, 500 and 600. Yes, the assumption were made. The value of KI was 250 and 500 and 600. Then all the KI values substitute into the equation. Then if given that the KP equal to 1000 and the KD is equal to 500, which is for the best get value. So as for the KI of the 250 of the substitute the KI, we get the function is 375S plus 62.5 and 16.1 S to the power 4 plus 8.2 times S to the power 3 and 9376 S to the power 2 plus 1562.5 S. So for these three value for 500 and 600, there is the same value of the 3 at the front here. Just the difference is the value of the back here, which is 1562.5 and 3125S and the 37750S. So we get all the value from the previous slide for the KI1 and KI 500 and KI 600, and the 150. We're using the MATLAB software to get the step response. This is the coding, and then produce the graph. So according to the graph shown here, all three graphs exhibit linear behavior when the PID control is applied. So there's a blue line is for TF1, which is 250, and the TF2 is for 500, and the P is for 600. This sorry for not very clear color here. Supposed to be here is a blue color, and then orange, red, and then orange color. So the graph for the P control and PID control are not basically the same. There are some difference. When looking at the graph of proportional gain, you will notice that the amplitude of the ABS system will increase in direct proportion to the amplitude of the proportional gain. So in contrast, the line graph of the PID control show that the amplitude of the ABS system increase in the direct proportion to the degree of PID gain. As a direct consequence of this, the use of the integral control has no impact on the responsiveness of the system. In general, it can be seen the incorporating all three controller P, I, and D into the ABS system is not really required. This is due to the fact that the graph produced here by each controller is identical, and thus take the form of the linear graph. And that's all from me. Thank you.
models becoming more complex as energy advances. So anti-lock brakes assist the driver in maintaining vehicles control in situations where heavy braking is required. So more research and more modification will need to carry out in order to obtain a more accurate data and specific results. So we have also learned that ABS have shown some advantage. So ABS technology significantly reduce the risks of your wheels locking and skidding, so especially in slippery conditions. So it is no exaggeration to say that it can be life-saving, helping to maintain control and to steer out the dangerous scenario. So ABS technology can keep your vehicle's insurance payments down precisely because anti-lock brakes have shown many times by lowering the risk of the accident. And lastly, for the recommendation, despite being widely used, anti-lock braking system may be improved due to their limitation. So to improve the anti-lock braking system, research and user feedback are needed to discover its flaw. So first, a lack of consistent data makes it difficult to establish the actual situation with the vehicle's crashes and ABS. So this study needs more harmonious national data sets. So next, the modeling approach makes certain assumptions that while necessary for the analysis must be evaluated to ensure the ABS within rate projection. So ABS should overcome higher braking distance on ice, snow, or soft surface. To improve ABS on wet, slick condition helps prevent accident. That's all for me. Thank you.